Hi guys, in this video we will explain about gray code, Hamming code, and logic gates.
History. Frank Gray, who became famous for inventing the signaling method that came to be used for compatible color television, invented a method to convert analog signal to reflected binary code grouped into tube-based apparatus. The method and apparatus were patented in 1953, and the name of Gray stuck to the codes. Gray was most interested in using the code to minimize error in converting signal to digital. His codes are still used today for this purpose. Binary to Gray. To convert binary to Gray code, bring down the most significant digit of the given binary number. Because the first digit or most significant digit of the Gray code number is same as the binary number. Number 2. To obtain the successive Gray code bits to produce the equivalent Gray code number for the given binary, add the first bit or the most significant digit or binary to the second one and break down the result. Next, to the first bit of the Gray second binary bit to the third one and write down the result. Next, the second bit of Gray code. Follow this operation until the last binary bit and write down the result based on XOR logic to produce the equivalent Gray code binary. Gray to binary. Number 1. To convert Gray code to binary, bring down the most significant digit of the given Gray code number, because the first digit or the most significant digit of the Gray code number is the same as the binary number. To obtain the successive second binary bit, perform the XOR operation between the first bit or the most significant digit of binary to the second bit of the given Gray code. Number 3. To obtain the successive third binary bit, perform the XOR operation between the second bit or the most significant digit or binary to the third MSD or the most significant digit of Gray code, and so on for the next successive binary bits conversion to the fine equivalent.
Is a set of error correction codes that can be used to detect and correct the errors that can occur when the data is moved or stored from the sender to the receiver. It is a technique developed by Irfan Hamming for error correction. Redundant bits. Redundant bits are extra binary bits that are generated and added to the information carrying bits of data transfer to ensure that no bits were lost during the data transfer. The numbers of redundant bits can be calculated using the following formula. Suppose the number of data bits is 7, then the number of redundant bits can be calculated using, thus the number of redundant bits is 4. Parity bits. A parity bit is a bit appended to a data of binary bits to ensure that the total of numbers ones in the data are even or odd. Parity bits are used for error detection. There are two types of parity bits. Even parity bits. In the case of even parity, for a given set of bits, the number of ones are counted. If that count is odd, the parity bit value is set to 1, making the total of count of occurrence of ones an even number. If the total number of ones in a given set of bits is already even, the parity bits value is 0. Odd parity bits. In the case of odd parity, for a given set of bits, the numbers of ones are counted. If that count is even, the parity bits value is set to 1, making the total count of occurrence of ones on odd number. If the total number of ones in a given set of bits is already odd, the parity bits value is general algorithm of Hamming code. The Hamming code is simply the use of extra parity bits to allow the identification of an error. 1. write the bit position starting from 1 in binary form, like 1, 10, 11, and 100 each. 2. All the bit positions that are a power of 2 are marked as parity bits, like 1, 2, 4, 8 each. 3. All the other bit positions are marked as data bits. Number 4. Each data bit is included in a unique set of parity bits, as determine its bit positions in binary form. A. Parity bit 1 covers all the bit positions whose binary representations includes A, 1 in the least significant positions, like 1, 3, 5, 7, 9, 11. B. Parity bit 2 covers all the bit positions whose binary representations includes A, 1 in the second position from the least significant bits, like 2, 3, 6, 7, 10, 11 each. Positions from the least significant bits, like 4 until 7, then 12 until 15, then 20 until 23. D. Parity bit 8 covers all the bits positions whose binary representations includes a 1 in the fourth position from the least significant bits, like 8 until 15, then 24 until 31. A. In general, each parity bit covers all bits where the bitwise end of the parity positions and the bit position is non-zero. Then 5. Since we check for even parity, set a parity bit to 1 if the total number of ones in the position it checks is odd. Then the last one, set a parity bit to 0 if the total number of ones in the positions it checks is even.
Logic gate has one terminal output and one or more input terminals. Output has a high is 1 or low is 0 value. Logic gate has 7 basic logic gates: AND, OR, NOT, NAND, NOR, XOR, XNOR. First is OR gate. The operation of OR gates are: if input A or B or both is high, then the output X will be high. If input A or B or both is low, then the output will be low. The form of OR gate can be symbolized as plus. So the formula can be written X equal A or B. This is the truth table of OR gate for 2 input. Second is AND gate. The operation of AND gate are: if input A and B and both is high, then the output X will be high. If input A or B, one of them or both is low, then the output X will be low. The form of AND gate can be symbolized as dot. So the formula can be written X equal A dot B. This is the truth table of AND gate. Third is NOT gate. The operation of NOT is not the same with OR operation and AND, because NOT operation using single input variable. The operation of NOT are: if input A is high, then the output X will be low. If input A is low, then the output X will be high. So the formula of NOT gate can be written X equal complement A. This is the truth table of NOT gate. X equal complement of A dot B. This is the truth table of NAND gate with 3 inputs.
Fifth, NOR gate. The operation of NOR gate is inverse from OR operation. If input A and B are low, then the output X will be high. Second, if input A or B, one of them or both is high, then the output X will be low. The formula of NOR gate can be written X equal complement of A or B. This is the truth table of NOR gate. 6. XOR gate. XOR gate is the short of exclusive OR. The operation XOR gate is: first, if one of two input is high, not both, then the output X is high. Second, if the both input is all low or all high, then the output X is low. The formula of XOR gate can be written X equal A XOR B. The truth table of XOR gate is 7. XNOR gate. XNOR gate is the inverse of XOR operation. The operation of XNOR gate is: first, if one of two input is high, not both, then the output X will be low. Second, if the both input is all low or all high, then the output X will be high. The formula of XNOR gate can be written X equal complement of A XOR B. The truth table of XNOR gate is